Right, so in this first question, it's asking us to complete the circuit diagram for the circuit that the student could have used to obtain the results shown in the diagram above. So clearly we've got something where the current and potential difference is varying, and we need to put a lamp into the circuit, and we need something that measures the current and measures the voltage as well. So using this battery, we're going to have a battery like so, and we need to have a lamp like so, and then we need to think about our measurements. So the first thing is, if we're going to measure the potential difference, we need to put the voltmeter in parallel, so that's going to go there. If we're going to have something to measure the current, then we need to put that into series, so we're going to put the ammeter somewhere like that. And the next thing is we need to change the current or the voltage, so we need to put something in that will change that, so we're going to put in a variable resistor. Okay, so this is what the circuit would look like. You're going to get a mark for having these different components: the bulb with a voltmeter, the ammeter, your battery here, and your variable resistor. Now it says, which lamp will be brighter at any potential difference? Explain your answer using the figure above to aid the explanation. Well, lamp A is going to be brighter, and if you look here at the same voltage of 10 volts, you've got a current here of just below, now in fact just above 0.3 amps, and this one here is about 0.75 amps. So lamp A has a greater current for the same potential difference. Now, why is it going to be brighter? Well, it's brighter because of the amount of power that's going through the bulb, and power is equal to voltage times current. And here we've clearly got the same voltage we just talked about for the same PD. So if this is the same and the current is greater on lamp A, then the power will be greater, because this is a directly proportional relationship. So the second part is saying the power is greater due to directly proportional relationship. I'll put an R for relationship. Okay, and that's based on this equation. Now it says lamp B has a higher resistance at any potential difference. Explain how this figure above shows this. So the lower the current, the greater the resistance. Okay, now if you remember that V is equal to IR, so R is equal to V over I, these two things are inversely proportional to each other. And because of this inversely proportional relationship, if we increase the current, we must decrease the resistance. That's what this relationship is telling us. In here it says both lamps behave like ohmic conductors through a range of values. Now, an ohmic conductor has a constant resistance. So V equals IR when R is constant. So when would we get a relationship where V is equal to IR? Well, this is a directly proportional relationship. So because it's directly proportional, we're looking for any part of the graph that is just a straight line. Now, according to the mark scheme, that is below 2 volts, but I think it starts to curve a little bit here, so I would probably go for around this range here. So you're going to go from 0 volts through to maybe 1.5. So 0 volts is a range through to 1.5 volts. Okay, so this is a filament bulb, and as you can see, when the filament bulb is switched on, the current surges a little bit, and then the current comes down a little bit, and then it normalizes, and this will be the current flow at normal working brightness. So it's asking, after 0.1 seconds, the bulb works at its normal brightness. What is the current through the bulb when at its normal? So we're looking for this here. Okay, and that's, if you draw a line across there, then you would have around 1.7 amps. Right, the bulb works at a normal brightness of 30 seconds. It is switched off. Calculate the charge that flows through the bulb. Now remember, charge, which is Q, is equal to current, which is I, times the time. So we've just said that the current was 1.7 amps and the time is 30 seconds, so that is going to be equal to 51, and the unit is coulombs, a capital C. Now calculate the energy transferred by the 12-volt bulb at this normal brightness. So voltage, or potential difference, is equal to the energy transferred, which is E, divided by Q, which is, as we just talked about, the unit for charge. So the definition for voltage is the energy transferred per unit of charge. That is what voltage actually means. Whereas current is the charge per given time, because if we rearrange this equation for I would be equal to Q divided by T. So current is the charge per unit of time and voltage is the energy per unit of charge. Okay, now we're trying to find the energy transferred, so we can just swap these two around, and therefore Q, sorry, we're not trying to find Q at all, we're trying to find the energy transferred, so we need to do E, which is the energy, is equal to voltage times the charge. We've got our charge here, which is 51, and the voltage is 12, so 12 times 51 will give you the energy transferred, and that's equal to 612 joules. Right, between 0.02 seconds and 0.08 seconds, there is an increase in both the resistance and the temperature of the filament inside the bulb. Now remember, in terms of resistance, with our wire, we have a metal ion lattice that looks like this, and these metal ions have free delocalized electrons moving around the wire, and when we put a voltage, say a voltage across here, potential difference of 10 volts, that causes the electrons to flow in one direction. Rather than randomly moving around the wire, they're all going to go in one direction around the wire. Now these metal ions, these positive metal ions in this lattice structure, remember this lattice is this grid-like structure, are constantly moving, but when they're heated they are going to move more, and that is really important when you're describing this. You would say, first of all, the metal ions in the lattice vibrate faster. So they're going to vibrate faster. If they vibrate faster, they're going to cause collisions with the free electrons that are moving through the wire. So as they move up and down at a faster rate, they're going to collide more frequently with the electrons. So with the second part, we're going to say, so the electrons collide more frequently. Okay? Right, for question 3, when you get one of these questions, the best thing to do is work out the whole thing, and then you can work out all the answers when you've finished. So, we know this is a series circuit. It's a series circuit because we can follow the whole thing round without any branches, without any other paths. So we know in a series circuit, if it's 2 amps here, it's going to be 2 amps everywhere. So I'm going to put 2 amps there, and I'm going to put 2 amps there, because we know that is the current value. It's the same all the way around the circuit. Now it's 18 volts here. That means these two things have to add up to 18 volts. So what we need to do is work out this using our equation, which is V equals IR. And if voltage is equal to the resistance, which is 3, times the current, which is 2, then we know 3 times 2 is 6 volts. Now if we know that's 6 volts, and this must add up to 18, then that has to be 12 volts. 12 plus 6 is 18. Now we know the voltage and the current here, we can rearrange this equation for the resistance. So R is equal to V over I. 12 divided by 2 will give us 6 ohms. Okay, so now we have all the values we could ever need, and we can answer all the questions. So the first one is, what is the PD, the voltage across X? Well, we worked that out as 6 volts. What is the potential difference across Y? Well, we worked that out as 12 volts, and using that, we then worked out the resistance. We know that one is 3, and that one is 6, and remember, in a series circuit, all we do is add the resistors together. So we've got a 3 ohm and a 6 ohm, so that gives us a combined resistance of 9 ohms. Okay, this next question I've left in, but is not on the combined unit. So this is only for triple science if you're doing separate physics only. So it says an 18-volt battery could not be used as the input of a transformer. Why is that? Well, it's a battery, and batteries are DC. Transformers require alternating current. They need an alternating current to generate an alternating magnetic field, and the alternating magnetic field will then cut the coil and generate an alternating current in the secondary coil. So remember, they do not work on DC. The transformer is 100% efficient, so because of that we can use the power equation if it's 100% efficient, and power is equal to voltage times current. So we know that the primary, this side, so we call that V1 times I1, must be equal, because it's 100% efficient, to V2 times I2. Okay, so what is the voltage on this side here? Well, it's 18 volts, so that's 18 volts multiplied by the current on this side, which is 2 amps, and that must be equal to the other side, and it says the voltage on the other side is 12 volts, which is there, and that is times by the current that we're trying to work out. So if we multiply these two, we get 36, and that is equal to 12 times I. So if we rearrange for I, then that's 36 divided by 12, which equals 3 amps. Okay, so for question 4, the first thing is, let's go through what they're trying to work out. So it says the apparatus used to obtain the data needs to calculate the resistance of a thermistor at different temperatures. So we've got a thermometer with a water supply to try and keep it as constant as possible, and the Bunsen is heating the water, and that's changing the temperature, which will then affect the resistance, because thermistors are affected by temperature, and that affects the resistance in the circuit. So it says in the box, draw the circuit for a thermistor. So remember, we draw a resistor like so, and then it kind of looks like a hockey stick inside the resistor. Use the data given in the figure 1 to calculate the resistance of the thermistor at 20 degrees C. So it's showing the water is at 20 degrees C, so we can now use V equals IR. And if we rearrange, R equals V over I, the voltage is 9 volts and the current is 0.02525 amps to there. Okay, so if you work that out, that is equal to 360 ohms. Now remember, the symbol for ohms is like that. Okay, so figure 2 shows the axis for a sketch graph. Complete figure 2 to show how the resistance of the thermistor will change as the temperature of the thermistor increases from 20 to 100 degrees C. So as the temperature increases, the resistance decreases. So you're going to get some kind of curve that looks something like that. So the resistance is going down as the temperature is increasing, but the resistance would never be 0, so just bear that in mind. You're never going to have no resistance, so you can't have the curve coming to this value here. It's never going to be 0, but it will be lower than you started with. Which one of the following is most likely to include a thermistor? Well, this is going to be for some kind of heating system, so we're going to tick that box there. The ammeter used in the circuit has a very low resistance. Why is it important that ammeters have a very low resistance? Well, if you think about an ammeter, it's placed in series with the circuit, so as the current flows through the circuit, you do not want the ammeter to have an effect on the current flow. So you need a low resistance so the electrons traveling through the ammeter are not affected, and therefore there's no heating effect as it moves through the ammeter. So ammeter does not affect the current flow. Okay. Right, it says scientists in different countries use the same temperature scale to measure temperature. Well, if different countries have different languages and they're all using the Celsius scale, then when they are producing any information, any results, and they all use the same one, there won't be any confusion, which is really important. Because if they measure the temperature to be 100, and one of them is in Fahrenheit and one of them is in degrees C, and you didn't know which one it was, then it's going to make a massive difference. Okay, so therefore when you're looking at people's results, they can be compared and there will be no misunderstanding. So it's for the comparison of results without any misunderstanding. Okay, sorry about that writing, it's really hard to write with this pen. Right, a student plans to investigate how the resistance of the light-dependent resistor LDR changes with light intensity. The student starts the apparatus shown in figure 2 but makes 3 changes. One of the changes the student makes is to replace the thermistor with an LDR. Right, so let's go back to what we were looking at before and we'll have a look at what they've done. So they've changed the thermistor and they've used a light dependent resistor. So remember, that's a resistor that is dependent on the light. The light is going towards the resistor. So that's change number 1. Now the next change is they're going to have some kind of light source. So we're going to change this Bunsen burner here. I'm going to use some kind of light source. So that's going to be our first change. Our second change is what we're going to use to measure the dependent variable. Well, we need some kind of light detector to change with the thermometer. So we're not measuring the temperature now, we're going to have something that detects the light here. Okay, so we put a sensor that detects the light. We can use a different light source, that could be maybe a lamp or a torch, etc. And we need some kind of sensor for measuring the light change. So we go back to our question. It said describe what other changes the student should make to the apparatus. Well, they should replace Bunsen with a lamp or a torch, and they need to replace the thermometer with a light sensor. Okay, right, this next question is about an electric cooker and it's asking us to calculate the resistance of one heating element, so just one of these. It says when all 4 elements are on, then the full power the hob draws a current of 26 amps and 230 volts. So that's basically saying around here the total current and voltage around these parts is 26 amps and 230 volts. So we need to use this to calculate the resistance. So we know that if V is equal to IR, that R is equal to V over I. So therefore 230 divided by 26 will give us 8.8 ohms. But that is the total resistance. So because this is a total resistance of 8.8, the resistance through each of these is going to be less. It's going to be 4 times less the resistance. Okay, so all we need to do is multiply this number by 4. So 8.8 times by 4 gives us 35.4. And the answer is to 2 significant figures, so we only need to use these 2 figures, so the answer is 35 ohms. Okay, so that's saying that that is 35, that is 35, that is 35, and that is 35. Now remember when we were doing 1 over RT is equal to 1 over R1 and 1 over R2, and I said when you're working out these values, you can use a system of equivalence resistance. So if they're the same, you could just divide these all by 4. So if we know the resistance of each resistor in parallel to work out the total resistance, we would divide by 4. But because we know the total this time, we need to multiply by 4 to get the resistance that way. So just bear that in mind if they ask you it in a different way. Right, so the table gives the maximum current that can safely pass through the copper wires of different cross-sectional areas, and it says the mains electricity supply using cables containing 25 millimeters square copper wires. So the cross-sectional area is 2.5, which means the maximum safe value is 20 amps. Now, in the last question, it just said 26 amps is for the whole of the heater, the hob. So therefore, 2.5 has a safe working value of 20 amps. We're using 26 amps, which is clearly higher than 2.5 millimeters squared cable allows. What would this do if you have a higher current, and this could cause a fire, so the wire could melt because the current flow is too great for the wire to hold. Mains electricity is an alternating current supply. Batteries supply a direct current. What is the difference between AC and DC? So AC, the current constantly changes direction. So it's oscillating. You get one of those waves, an AC wave like that, because it's going forwards and backwards in the wire. So if this was our wire, the electrons would go forwards, backwards, forwards, backwards, forwards, backwards, constantly changing direction. DC, the current goes in one direction. Now remember, we're talking about the current here, so don't just say AC constantly changes direction. You need to say the current constantly changes direction, or DC, the current goes in one direction. An example of this is the mains, remember, which is at 230 volts and has a 50 hertz frequency, so it's changing direction 50 times every second. And DC is a battery, and in a battery you get the current going one way around the circuit. Okay. Right, in this next question it's asked us to draw a symbol for a diode and a variable resistor. So a diode has the triangle pointing in the direction of the current flow. We put that into a circle and it looks like so. A variable resistor is a resistor with an arrow like that. So variable resistors are able to vary the resistance or the current flow, and diodes mean that the current only flows in one direction, so the current would be flowing in this direction through the circuit. The reason for that is because they have very, very high resistance the opposite way. So the resistance is lower that way, and in the opposite direction the resistance is so high that it's not going to allow the current to flow the opposite direction. Right, the student made two mistakes when setting up a circuit. What mistakes did they make? Well, if you look at this diode, you're trying to measure the energy change across it, the potential difference or voltage drop, and therefore this should be a voltmeter, and we always put in series an ammeter, so that should be an ammeter and that should be a voltmeter. So the ammeter is in parallel and it should be in series, and the voltmeter is in series and it should be in parallel. Okay, so the voltmeter should be there and the ammeter should be there. Okay, make sure you use these terms though. The ammeter should always be in series and not in parallel, and the voltmeter should always be in parallel and not in series. Right, at what potential difference did the diode start to conduct? Well, that's around here, so that's 0.2 volts. Use data from the graph to calculate the resistance of the diode when the potential difference across the diode is 0.3. So at 0.3 we've got it there, and if we go across, then if I draw a line across, it should end up there, sorry, which would be more accurate, and that is 0.008 amps. So 0.2 divided by 0.08 is going to give us our resistance, and that is equal to 37.5 ohms. Right, so the next question has to calculate the frequency. So each horizontal division of the oscilloscope represents 0.01 seconds. So what does this mean? Well, this is a time period, and the time period is the time it takes for one complete cycle or wave. So if each division represents 0.01, then that means from here to here is 0.01. So from here to here is 0.02, to here is 0.03, and to here is 0.04 seconds. So we're starting the wave, we're going up, down, and back to where we start. So that is one wavelength, or the time period for one wave. Okay, so that is 4 times 0.01, and that is equal to 0.04. So if the time period is 0.04 seconds, then frequency is equal to 1 over time period. So this is a reciprocal, the reciprocal of 0.04, so 1 over 0.04 is going to give us the frequency, and 1 over 0.04 is 25 Hertz. Okay, why does a diode cause the trace on the oscilloscope screen to change? Well, the reason for this is a diode will only allow the current to flow in one direction. With an AC current, we've got positive, negative, positive, negative, positive, negative. Okay, so above the line is our positive value, below the line is our negative value. And this means, just like velocity, the electrons are going in one direction and changing direction constantly. And this is the frequency of the wave. So what does the diode do? Well, it only allows it to go in one direction. So you're not going to have this bottom half of the graph, you're only going to have a positive value. So this is what the diode is doing. It's only allowing the electrons to flow in one direction, not the opposite direction as well. Why does it do this? It's because the diode has a very high resistance. So remember when we drew our circuit symbol before, we said the arrow represents the direction. Against this diode is a very, very high resistance. So the current cannot flow in that direction, or the current that would flow would be so low it would be insignificant and you would be unmeasurable. Okay, so what's the answer to this question? Well, it only allows current to flow in one direction. I'm going to put D for direction. In this case, positive PD, and that's because of the high resistance in opposite direction. I'll put D for direction. So on the negative value here, where you get this part of the graph, the resistance is so high it doesn't allow the current to flow that way, and that's how a diode works. Right, the next question, the diagram shows two oscilloscope traces. It's got trace A and trace B. It says describe how the potential of the live terminal varies with respect to the neutral terminal of the electricity supply. Well, you can see that this is going negative, positive, negative, and positive, and the neutral wire should really just stay, sorry, that's a really bad line, it should stay at 0 volts with respect to the live wire, which is constantly going from negative to positive to negative to positive. Okay, so how are we going to describe this? Well, all you have to say is that it alternates. Remember, it's alternating current, so it alternates between positive and negative values. What does trace B show? That is showing the neutral wire and the voltage between neutral and the earth. Okay, so you've got the neutral wire and it's connected to the earth, and therefore the voltage between these two should really be around 0 volts. So it's the difference between the neutral and the earth. Okay, right, what is the period of this electricity supply? Well, we just said that you need to work out the time period based on a division, and if each division is 0.005 seconds, then we need to know how many divisions there are. So for starting here, we've gone down and back up and down to here again, and that is 1, 2, 3, 4, 5 divisions. So 0.005 times by 5 gives us our time period, which is 0.025 seconds. Frequency is equal to 1 over time period, so therefore 1, our reciprocal of 0.025, is going to give us our frequency, and that is equal to 40 Hertz. Right, the next question. So we've got a circuit, and this is for the headlights on a car, and you can see that these are in parallel to each other. So the lamp here is in parallel to this lamp here. The current through the filament lamp of one car headlight is 3 amps. So we know going through here is 3 amps, and going through here is 3 amps. So we would expect going through here the current to be the sum total of these, so we would expect it to be 6 amps. So a suitable fuse would have to be something that is greater than 6 amps. So anything greater than 6 amps. Now normally the fuses are 3 amps, 5 amps and 13 amps. So you could pick a 13 amp fuse, but there are fuses that exist at around 6-7 amps. So to be safe, I'd pick a 7 or 8 amp fuse. Right, calculate the resistance of the headlight filament when in use. So I don't know why it's got watts here, but that should be in ohms. So resistance, so we know that V is equal to I times R, and we know that R is equal to V over I. So it's just one headlight filament. So we know, because it's a parallel circuit, for parallel circuits the rule is that 12 volts goes into each branch. So we know that's 12 volts, and it's going to be divided by 3 amps. So 12 divided by 3 is 4 ohms, so the answer is 4. Right, calculate the power supplied to the 2 headlights of the car. Power is equal to voltage times current, or it's equal to I squared R. So it could be the voltage of 1, which is 12, times by the current of 1, which is 3, or it could be I squared, which is 3 squared, which is 9, times by the resistance we just worked out, which is 4. And both of them should equal the same thing, and they do, which is 36. That would be 1 lamp, so you need to multiply that by 2 to get 2 lamps, and that will give you 72 watts. Right, the fully charged car battery can deliver 72 kilojoules. Remember, this is in kilojoules, so we need to convert it. So we're going to do that and say that's 72,000 joules of energy at 12 volts. Now we know that the power is equal to energy divided by time. So if we're trying to work out the energy, then that must be power times time is equal to the energy. Our power we've just worked out as 72 watts, and we're going to we're trying to find out the time here. That's not right. So we know that the time is equal to energy divided by power if we rearrange these two. So if the energy is 72,000 and we divide that by 72 watts, which we said here, we can just cancel those, and that will equal 1,000 seconds. Right, the last question. So describe the difference between AC and DC. So I said before, AC is constantly changing direction. And DC is one direction. But you must say that the current constantly changes direction and that the current moves in one direction. It's asking about the current, so make sure you use that in the description. Right, and the last question, it's talking about how an earthing system works. So it says if a fault makes the metal case live, so normally the electron flow is through the filament bulb, and this has a path of very high resistance. So the reason this is getting hot is because the filament has a high resistance because of the material it's made out of, and therefore it emits lots of heat energy because of its high resistance. Now, if for some reason the live wire became connected to the metal casing, because the earth wire is also connected to the metal casing, the current would no longer flow through the high resistance filament bulb. It would go down the lower path, or a much higher current flow would go down the path of lower resistance. So because the path of lower resistance, the earth wire, if it has lower resistance, then you're going to get a higher current flow down this earth wire. So the earth wire offers a path of lower resistance. Because of this lower resistance, you get an increase in current flow. If you get an increase in current flow, then when the current flow, because it's still going down the live wire, the increase in current flow going through the live wire is going to blow the fuse. Remember, the fuse is attached to the live wire, so this increase in current is going to blow the fuse. So that's what you need to say for this last answer. And here is the mark scheme